Okay, welcome everyone to my sixth lecture on quantum topology without topology. So the goal for today is slightly different than what we have seen, or the goal for the next five talks actually is slightly different than from what we have seen before. So basically, I want to do now, I want to discuss more the linear algebra part of quantum topology. So in the end, all those topological notions are really, really nice and they're easy to imagine, they're nice to play around with. But in practice, in the end, they're pretty tough, they're pretty hard. So I skipped over all of those proofs that my diagrammatic categories are, let's say, equivalent to cobordisms and whatsoever. And yet, and it turns out that topology usually is pretty hard. It looks very innocent, but actually it's pretty hard. And the main approach of mathematics in this case is kind of a general approach is to find some nice invariants, right? So some nice, more like a numerical datum, a number that you can assign to some topological object that will tell you a reasonable amount of information about the topological object. And remember that last time, basically, I wanted to say that the quantum invariant is some functor from some nice topological category. Also, topological for me means it comes disguised as some Brouwer category thing to some linear algebra-like category. Okay. And in order to understand what that means, we need to discuss kind of the analog of linear algebra in categories. And this is where the notion of additive, linear, and abelian categories comes up. So basically, what I want to discuss is what is the analog of linear and the analog of homological algebra in categories. And it will turn out that linear algebra is easier than homological algebra, right? And linear algebra in categories is easier than homological algebra in categories. So homological algebra in categories is a bit tricky, in particular if you see it for the first time. So just stay with me. At the end, I'm trying to make everything kind of explicit using a lot of examples. But it looks pretty difficult if you see it for the first time. And this is usually phrased in terms of abelian categories. So homological algebra is kind of abelian categories, and linear algebra is more like additive and linear categories. And they're much easier to define than abelian categories. So we will see this. I will start, of course, with the easy ones, with the linear categories, but at one point we can't avoid talking a little bit about abelian categories as well. Yeah, there will be a lot of conventions that I will use. Well, it's not so important. One of them is the only one that is really important is that I write this funny symbol here. So S, this bold S, which I actually really can't write, something like this, for a ring. That's basically a commutative ring. So if you don't like the notion of commutative ring, then you can think of S as being something like the integers, any field you like, whatever, the real numbers, something like that. It doesn't matter so much. I just read S because bold R is already read. It's already taken by the real numbers. So that's fine. Why I have this funny notation. But S is a ring. Okay. And K usually is a field. So this is a field. And this is a ring. This is, again, it's slightly weird notation for a ring. But bold R is already taken by the real numbers. So whatever. The best approximation to R is S, if you want. Whatever. Anyway, so S and K will be rings and fields. You can think of integers or whatever you like. It won't be. Uh, Usually, it is not of huge importance. Okay. So I want to start with kind of, well, we have seen the standard product structure, and I want to start with my good old friend vect K. And the standard product structure on vect K was kind of a multiplication, right? And the question would be, what is kind of an addition on vector k? And I will use the usual symbol for this, for the direct sum, which is a, so tensor product is a circle with a cross, and direct sum is a circle with a plus. And let me try to motivate the definition along this example of vector spaces. And in a second, even much more explicit in its skeletal incarnation, or at least these skeleton of finite dimensional vector spaces for matrices. And matrices will be kind of my running example throughout anyway, because all these notions that I'm going to show you, as I said again, they might look very scary at first point, but they are really just, you look at vector spaces very, very hard. You like vector spaces a lot, and you kind of generalize what's going on. Anyway, so keep vector spaces in mind. So what do we want to note? Well, we will note the following. Home spaces and vector spaces, right? These are matrices. They actually have extra structure. They're not just sets, right? Matrices have extra structure. They're not just sets. And what kind of extra structure do they have? Well, they are themselves actually k-vector spaces, right? You can add matrices, you could scale up, multiply matrices. In a slightly different language, you would say they are abelian groups. Because whether you write, so abelian groups just means Z modules, right? Oh, that was really bad. Let me try again. And so whether you write K vect or Z mod, not a big difference. But anyway, they are abelian groups. So it means you can add matrices. F plus G is still an element. So F is a morphism, G is a morphism, F plus G is still a morphism, right? There is an additive unit, there's a zero map, there's an additive inverse, minus F, and slightly less obvious, but well, they're actually completely obvious, but maybe it's not the first thing you would write down is composition is actually bi-additive. So these are the points, right? So it's an abelian group. You can add things. There's a unit, a zero. You have additive inverses, and slightly less obvious. Your composition is bi-additive. Yeah, and the remark is just saying what I just said. There's a slight difference between Z linear, which is an abelian group, and K linear, which is slightly. Well, maybe I shouldn't use K linear, which is a slightly different. The difference won't matter. It's kind of a matter of what you like as scalars. So, but just keep in mind, abelian group means C linear. So abelian groups. So this whole nonsense here is C linear. Not C linear, Z linear. So over the integers. Okay. So all I said is that home spaces are abelian groups, basically. And we have in vector spaces, it's kind of pretty clear that home spaces are abelian groups. Okay, we're still in vector spaces. There is a zero object, the zero vector space. Right? And I will denote the zero object by this symbol here. And what makes the zero object interesting is, well, for the zero object and any other, so this property 661, for the zero object and any other object, there exists a unique morphism into the zero object and from the zero object. And the unique morphism is, of course, a zero map. But in the categorical language, you don't really know what a zero map is, so you just say there exists the unique morphism. Okay. There exists the unique morphism into the zero object and from the zero object. And we call this morphism, well, in this case, it is just a zero map, of course, because, well, what can you do if you map from or into the zero vector space? So this is just, of course, the zero morphism. Yes, it's just a zeromorphism, as I said. Um, and yeah, there's zero maps. Again, not a really exciting observation. It's just that's just what it is. Um, Third property, slightly less obvious if you write it down, completely obvious, of course, but slightly less obvious to think about, is that you have you have a direct sum operation, and yeah, it's just what it is. A direct sum of a vector space is just a direct sum of vector spaces. So, if you want an explicit example, k plus k is of course just isomorphic to k squared, right? Um, Not well in matrices. It's actually nicer. The matrices will be down here, so just bear with me. Stay with me for a while. We will go to matrices in a second. But abstractly, the direct sum. This is exactly the operation. Direct sum. Has the following properties. So here's my direct sum of x and y, and I have x and y, and I have morphisms, which I will call inclusions, that are the i's, and which I will call projections. These are the p's. And the morphisms, well, they do exactly what you think they do. So px goes from x from the direct sum to x, and py goes from the direct sum to y, and the inclusions go there in the opposite way. And you observe that the following holds: if you include x, you include it into the direct sum, and then you project down to x, then this is actually the identity. Similarly, the other way around, just for y. I mean, there is no way to prefer x over y here, right? This is slightly less obvious, the last property, if you just do it the other way around. If you see it in matrices, it's obvious. So just bear with me for a second. So x plus y. So how can you create the identity on x plus y? Well, if you go down to x, you certainly lose the information of y, right? So let me make this in a different color. Green. Green is good. Maybe dark green. Okay. And if you go down to y, you also certainly lose information. And the way to not lose information, let me make this in whatever, black. The way to not lose information is to sum over both ways. Okay. This was really bad. So take the sum over both ways. So basically, I want to put a plus here, and then I go back, using the inclusion and using the other inclusion, and I go back. Right. So going each way separately, you would lose information. So you kind of go both ways at once, and you end up with this condition. So this is always kind of a decomposition of the identity. And let's have a look at matrices, because for matrices, this is really super obvious. So even more down to earth motivating example matrices. So remember that matrices, this was this category where the objects are just numbers, and the morphisms are matrices of the corresponding sizes. And the first bullet point from above here, this abelian group thing, on matrices, it's just, well, you can add matrices, and addition is bilinear with respect to multiplication. And this just means if you multiply with, let's say, two parameters and compose, then you could compose first, and you can pull out both parameters because it's bilinear. Right? Yeah, I mean, yes, this is all. This is what we learned about multiplication of matrices. That's certainly true. The second bullet point from above is the existence of the zero object. Well, there's certainly the zero number. Remember, the objects here are just, so objects are, as I said, just whatever numbers, 1, 2, 3, blah, blah, blah. there's certainly a zero number, and there's certainly a zero matrix. Okay, and the zero matrix exists for a kind of uh, you can also have a zero column matrix, whatever, which would be, or a zero row matrix, depending which one it is, which would be the matrix here from x to 0 or from 0 to x. Okay, so this is easy. This is also easy. And now let's have a look at this one. So the direct sum is, of course, exactly what you think it is, like 2 plus 2 is 4. Remember, this is strict, so 2 plus 2 is really just 4. It's just another way of writing 4. And the inclusion maps and the projection maps are, again, what you think they are. So the inclusions and the projections are the corresponding row or column matrices, which are just split into two blocks corresponding to to this decomposition of 2. Of course, you can do that, right? And you can check that if you do them in the right order, then exactly this graph here holds. I shouldn't have said this graph. Exactly these three properties hold. Okay, my motivating example. And now we want to formalize this, right? Before we can do that, a brief reminder on universality. Okay, it works as follows. And the best way to learn universality is to do as many examples as possible. Let me just briefly go through it, and then let me focus on this example. So, the general setup is as follows, or the general setup I want to use is as follows. There's a factor between certain categories, f. Good. And we kind of want to have a universal property with respect to f. Okay, good. And universal property with respect to f is basically you have a pair. You have a pair of an object x, and x is from C, and a morphism f. And f goes from some object y to f of x. Okay? So the pair consists basically of x and f, and the input is, let me do this, y and f. Right? As soon as I fix those things, that's what it is. It's a pair. And this is why it's called the universal property for f and y, for y and f. Okay, so a pair consisting of an object and a morphism. Object and the morphism. And the universal property is then just saying that for all maps, well, let's look at the diagram. So what you can do is you can write your f here in the first row, and okay, and you want to go to you have some fixed g. G goes here. Okay, and then there is some u, and it goes from x to z. From x to z. So so let me do it this way. Okay, so we have our f. That's our choice. Okay. And we have fixed some map G, which goes to f of z. And that G. And there's one way you could think of to make this diagram commute. So you want to write down something. And the something is this f of u. And the universal property is saying that this u is unique. So after you've chosen G, this u is unique. There exists the unique u making this diagram commutative. And that's the universal property for y and f. Let's say it again. The universal property for y and f is the choice of a morphism, of an object and a morphism, such that for each blue choice here, so I choose something blue, my G, I can fill up the corresponding commutative diagram uniquely. I can fill it up uniquely. So there exists a unique, whatever, making blah, blah, blah commutative. And absolutely similar, just just for op categories. There's also universal property for f and y, just reversing all errors. Right? The universal property for y and f is using a morphism from y to f, and the universal property from f for f and y is using a morphism from in this direction, from f to y, the opposite. Okay, so let's try to understand this in an example. And the easiest I can do right now, because I haven't introduced direct sums yet, direct sum will be an example, is the nonlinear version of a direct sum, and that's the Cartesian product of sets. So x cross, or x1 cross x2. Okay. So what we need to do is, in order to have something universal, we need to fix a factor. And the factor I want to fix is a very easy factor. It's called the diagonal factor. So it sends x to x cross x. Okay, the diagonal factor. And the point is, this thing here will satisfy universal property. Right? It will satisfy universal property, and it will be universal property in op actually. So it will be the opposite diagram. So let's try. So this thing satisfies universal property. So the first thing you would do is you would write down a map from um, I should have called it x and y. I don't know why I called it x1 and x2. Anyway, you would write down, you would fix a map from here to here. Okay, not quite, right? Not quite. We are in the opposite. So you would need to fix a map from in the other direction. This guy, however, because f is the diagonal factor, is just this one, right? It's just a double pair. Nothing really scary. So this is our choice of f from above. So this was f. And the coordinates of f is just the projection and the projection. So either the first or the second coordinate projection. Okay, so let's have a look here. The next input was a blue map, G, a blue morphism, a blue arrow, G. Now in the opposite order. So here's my f prime. Okay, I shouldn't have called it f prime. I should have called it G. But anyway, here's my f prime. So it starts from some object and it goes somewhere, and it's just fixed. It's just some map. And you're wondering whether there is a unique map that makes this diagram commutative. So does this red one exist? Or is the red one actually, and so this red one should be an f of something, right? So does this exist? And yes, it does. There exists a unique map from Z into the Cartesian product that makes this diagram commute. That if you have a map from here to here, you can certainly find a map to the double thing such that you can go back. Because you can't lose information, right? You have projection to one and you have projection to two. Yeah, I mean, I think really the only way to learn those properties is to stay at those for long enough, and then you will realize it's not so hard. But really the point about having a universal property is that I would try to learn some examples. Here's one, try to understand it, and then so in a lot of cases, something will satisfy universal property. It is completely fine to just think, oh yeah, it satisfies universal property, so what can I do with it? It might be a pain to verify that it satisfies universal property, but in a lot of cases it's well understood. So let's just assume that this is true, and let's just see what we can do with it. And the point of universal properties is the following lemma, which I don't have much time to go into it. So I hope you would like to read it because it's not so bad. But the statement is, as soon as you have a unique property, and if if something exists and satisfies the unique property, so this is crucial, okay, a crucial input. The existence. The universal property basically tells you it is unique if it exists. So that's what this lemma says. Then so basically what it says, it is unique up to a unique isomorphism. If it exists, it is unique. Something defined by a universal property is as unique as it can be. It just needs to exist. Okay? It might not exist at all. But if it exists, it is as unique as it gets. And the argument is a diagram pasting argument. It's actually pretty nice, but I just, well, just try to read it yourself. It's probably nothing you, maybe, yeah. It's, you basically apply it twice. So it works as this. Let me just do it. Okay. I'm losing time. I will have to be faster at the end, but anyway, it's a nice argument. So the way to prove it is, well, assume that's another pair. So we have two pairs, our starting pair and our, well, some prime pair, and they both satisfy the same universal property. And what you can then do is just to paste things together. Yeah, maybe this way. So X and F satisfy universal property. So my blue choice here, and you can just take F prime. Okay, so there exists a unique whatever making this commute. Good. And okay, so this little part of the diagram here is here, or this part rather. All right, but now you have also the universal property for F prime, and you can choose F. And then there exists the unique thing making things commute. Okay? But then, okay, then you have this double triangle-like thing. So maybe I should do it this way. The yellow one is the one coming from the universal property of X and F, and the blue one is the one coming from the universal property of the prime versions. Okay, so paste them together. And it turns out, of course, just composition tells you that there is now there's certainly a map of from f1 from f of x to f of x, and you do now the following funny trick. You can use f itself as a blue morphism. So f is the blue morphism G from above. And universal property tells you there's a unique map filling this in, but since there is the identity map is a unique map, so the identity map is a map that you would write down here. Okay, and then you realize, oops, if this is the identity map, that this composition actually is invertible. So so this is H and H prime. So you have found actually a invertible, so H and H prime are invertible and unique. So you have found a unique invertible map from X to X prime and from X prime to X, such that everything works. Okay, it might have been a little bit too quick. Don't worry, just read the argument once more. It's not so hard. So let's say it again. You have two universal properties and you paste them together. And because there is this uniqueness built in, everything will be forced in the end to be kind of equal to the identity. And that's usually very good because it tells you that something is invertible. That's all that happens. All right. And the point, okay, let me say again what the point of this universal nonsense is really that they are unique if they exist, right? So that's the whole point. So extremely important. And they are, again, as unique as it could be. They're unique up to unique isomorphism. It can't get any better. This is as good as it gets. The problem is they don't exist in general, and we will see that. So this is great. So green is great. Uh, uh, this is kind of bad. Right? The good, the bad, and there's probably some ugly somewhere as well. At the moment, we only have a good and a bad. So good is the green one. Um, and it usually, if something exists, then you can play a lot of games, and then it boils down to proving that something exists. Okay, I'm already really doing bad on time, so let's just move on. Just remember that what I want to do is I want to do linear algebra in categories, and there will be the corresponding notion of direct sum, and there will be homological algebra in categories. There will be corresponding abelian things, and almost everything will be defined by universal properties. And the only thing, universal properties are nice in the sense that the only thing you need to do in the end is to check that they exist, because if they exist, they are unique and satisfy basically everything we want. That's why people like to formulate everything in terms of universal properties, because then you kind of have a blueprint map of how to prove things. So if you have some universal property, proving something about it is in a lot of cases just a very standard diagram pasting argument. So you take your universal property diagram and paste it together in certain ways, like I did here. So this is kind of a standard blueprint of a prototypical example of how proofs work with universal arguments. Anyway, this was probably too quick anyway, so just read it again, and let's just jump into it. Something that is much more explicit and not very hard. Just keep in mind that we had those two examples, vect and matrix, so vector space and matrices. And everything below is really just a generalization of what you have seen above. Let me just recall what you have seen above. That's for matrices. You can add matrices form an abelian group. You have a zero matrix with a zero object. Okay. And you have this block decomposition. That was the direct sum. Okay, so let's try to generalize this. I call a category S linear if the home spaces form an S module, and composition is bilinear. That's exactly what we have seen above, where S was Z above, right? This was this abelian group. A Z module is an abelian group. I could just do the same definition over any ring. So any field, any ring, whatever you want. The very simple definition. This just means you can add more. Basically, this means you can add morphisms. And being bilinear, the composition being bilinear is a coherence condition for the two operations that you have now, addition and composition. Okay, good. So S linear. Vector spaces are K-linear, right? K vector spaces are K-linear. And I call something additive if, well, the minimum requirement I would like to do is it is Z-linear. Okay, so home spaces form abelian groups. It's exactly what I've done above. There's a zero object, and there's a direct sum, which satisfies this crap here. And this is already written in a general sense, and this is a universal property. Try to think about why this is a universal property, but direct sum should satisfy this. So there will be projections and inclusions satisfying, well, the projection and inclusion, well, rules, whatever they want to call them here. So those things that I've written here, this one and this one. This one, of course, for y as well. So whatever. But it's really just the same as for vector spaces. You can do this definition in general. Um, okay. So let's look at some examples. Kind of the point is that this part of mathematics is not based on sets. So set is not linear, it's not additive. Vect is. Vect is the linear version of set. So it's kind of a linearization of something. You will see this later in a second. Well, not in a second, but maybe in 5 minutes. So set is neither linear nor additive. Okay? It's not that bad, but it's not neither linear nor additive. Obviously, just think about it. There is no linear structure, no scalars on sets. You would be very surprised if I tell you that vector spaces, finite dimensional vector spaces, basically any version of vector spaces are k-linear and additive, and I just call this k-linear additive. So k-linear is a slightly stronger property than being z-linear, because now I have scalars over a bigger field, a bigger ring. These funny versions that I've shown you before, this graded vector space is my favorite kind of toy examples. They are by definition linear, but they're not additive. I never told you anything about a direct sum in those categories. That's a problem we will solve in a second. It's not a big deal, but by definition, they are only linear and not additive. On the other hand, what color to use? Let's use this one. Vect Z. This is just abelian groups. I just like to write down Z modules, right? And I never really understood why people like to. Well, I do understand, but I'm not a big fan of distinguishing the notion of a vector space in the module. Whatever. Let's forget it. So for a ring, I usually also say it's a vector space of a ring. So that's why I write vect Z. But strictly speaking, it's just Z modules and not Z vector spaces. Anyway, and this is not k-linear for any field by definition, because there are no scalars beyond the integers. Okay, of course it's z-linear by definition. All right, so basically versions of vector spaces are linear or additive in one way or the other. And this example is also a little bit funny, so let's do it. It's pretty easy, nice. So additive categories need to be closed under direct sum. Okay? Yeah, that's basically the definition. So you can always take the direct sum of an object is always in your category. And then you can play a following game. So you can take even dimensional vector spaces, infinite dimensional vector spaces. I call it even vect. And you will realize, ooh, they are k-linear and additive. Huh? Why? Okay, the only thing you basically need to check is that an even dimensional vector space, direct sum an even dimensional vector space is an even dimensional vector space. And the only thing you really need to observe here is that even plus even is even. On the other hand, well, clearly there's also the subcategory of odd dimensional vector spaces, but this is not additive, right? So not additive. And I write plus for additive. Why not? Well, because odd plus odd is even. So you would run out of your category. It's not additive. It's still k-linear, of course, but it's not additive. Okay. Okay. Yeah. Okay. This lemma is just saying that the direct sum is a bifactor. That's easy. And this lemma is just saying direct sum is satisfies the universal property, so it's basically unique up to unique isomorphism. And that's why I usually like to say the direct sum. Okay, not a direct sum. Okay, let's just because we are doing really bad on time, let's just run through the usual yoga very quickly. I hope you're used to the usual yoga by now, and this is okay. So let's just do it. Of course, if you have all these notions, then you can define it as linear functor, which is exactly what you think it is. The induced map is S linear. Okay. A little bit funny is you would think you would need to define an additive functor, but it turns out that um, a linear functor between additive categories is automatically additive in this sense. So additive would just mean f of x plus y is isomorphic to f of x plus f of y. But you have this extra structures. That's exactly what you would do with it. And yes, it works out. This is actually pretty nice. It's very easy. You just write it down. You can have a look at the proof. But it's a bit surprising. Like linear is the right notion for additive categories as well. It's a bit surprising. Linear is certainly the right notion for linear categories, but it's also the right notion for additive categories. And really, the slogan is linear implies additive, right? In this case. All right. And then we run through the usual yoga. Surely the additive factor is linear. The additive factor, the identity factor is linear. Composition is linear. So you get a category of linear categories. And I denote this by cut S. And similarly, you get the category of additive categories. And I denote this by cut direct sum. And you get the well, of course. The point is, by this lemma, the appropriate notion of functors are in both cases are linear functors. But this is kind of the only really thing to take away here. So linear functors are the right notions between additive categories as well. Obviously, they are the right notions between linear categories, but they're also the right notion between additive categories. Surely, if we have linear categories and we have additive categories, then we have also linear additive categories and cut as direct sum and the corresponding functor categories. I hope this wasn't too quick because I've done this several times by now. It's kind of usually yoga, right? You have a new notion on categories, you cook up the corresponding notion on functors, you cook up the corresponding categories of functors and categories of categories. One thing is missing in the usual yoga, and this is equivalence. Equivalence of S linear, let's say S linear additive categories, denoted by S and plus. Similarly, of course, for linear categories or for additive categories, is yeah, it would be using a linear additive factor. Right, really just the usual yoga, so nothing scary. Okay, so now comes a slightly new topic. So let me recall what we have seen. Um, Generalizations of the notions of block matrices, basically. So direct sum in arbitrary categories. Slightly different. There's a notion of linearity in arbitrary categories. Taking both together, you get linear additive categories. The only examples you really need to keep in mind are vector spaces. That's the main example of additive linear categories. And you have then I just did the usual yoga, like cooking up functors and functor categories, linear, additive, whatever. Nothing really new, I hope, for you. If you made it to this point, it's hopefully not new, completely new to you. Okay, and the question is actually how restrictive are those notions? how restricted is it to be a linear category? Are there many linear categories? How restricted is it to assume that you have an additive category? Are there many additive categories? Um, and the answer is it's basically no restriction at all. This is really exciting, really, really good. So I call this a linear extension and the additive closure. And it really allows us to perform linear in algebra in almost all categories. Okay. So linear algebra, this is really saying, right? So as soon as you have, I mean, everything is, you haven't seen it at this point, but everything is built on matrices. So as soon as you have additive linear, you should be able to perform some linear algebra, right? You should do some Gaussian elimination and whatever you know, linear algebra. And it turns out that it's not a really restriction. You can always kind of linearize everything. And this is really amazing. I mean, that's really saying that in some sense, that linear algebra is a very, very basic and general concept in mathematics altogether. Let me run you through it. And it's important, so I'm trying to be slow, and then I need to hurry a little bit again at the end. We'll see. We'll see how it goes. There's still quite a few pages to go. Um, so the linear extension of a category, and I call it, well, CS, if I start with C and the S linear extension, S is some ring, is just the following. Home spaces in this new category is the free vector space generated by morphisms um, on the other category. You will see this in an example in a second. Basically, for any morphism, you also define a morphism which has a scalar in front. Right, that's what I write here. In words, the home spaces are the free S modules, vector space, whatever, with basis sets being the corresponding home spaces in your starting category. And that's called the S linear extension. Right? Take the home spaces and add scalars. That's all I did. Nothing really fancy. Yes, and that is right. So the K-linear extension of sets is vector spaces. That K-linear extension of sets is vector space. That just means, why on earth should I stay with sets? I can always go to vector space, and it's really no loss of information. You just have now a little bit of linear algebra to play around. So vector space and sets are basically the same things. The linear extension of the other of one is the other. The linear extension, okay, this is a slide of a silly example. So we had this graded vector spaces, and I did two versions of it, like the non-linear version and the linear version. And yeah, the non-linear version, the linear extension of the non-linear version is the linear version. It's much funnier. It really, it kind of pretty confusing if you see it for the first time, but it's easy and very powerful, is to have a linear extension of diagrammatic categories. And for all of them, it works in the same way. So let's just use the easiest one, or maybe not the easiest one, but kind of my standard one, the Brouwer one. So where I just draw those diagrams, right? Whatever, these things. Yeah, looks good. And this just means now, well, so let's say my scalars are from Q. Why not? Doesn't matter so much. So I can write whatever, 2/3. Good. Then the new elements, the new morphisms in my Brouwer are just linear combinations of diagrams, like 55/12 times the crossing, minus 2/3 times the cupcake. Okay? These are my new morphisms in Brouwer. And the only requirement I have is because of this condition, things that I add are always from the same home space. So this doesn't make sense. In Brouwer, this just means things that I can add have the same starting points and the same endpoints. But if they have the same starting and endpoints, I can just add them as much as I want. But, all right, I can just add as many of them as I want to. Well, finitely many. I would take finite sums, right? We're in the linear setup. The setup of vector space, you only take finite sums. Or said otherwise, we're doing algebra, and nothing where you have to take limits. Anyway, point is any weird combination of diagrams with any kind of scalars you can imagine, yes, that's legal, as long as endpoints match. Okay, so here would be, for example, one of these elements. This is just this one. You can have another element which I call 12 times the cup, and usually you would say, okay, I could compose a cup with a crossing, and this would give me this thing, and I could compose a cup with a cup cap thing, and this would give me whatever, this guy. And I can still do the same. I just have to be careful with the scalars. And the only thing that happens now is this is bilinear. So composing 12 times a cup with this crap here gives me 55 times the first one. You do it, right? You do it linear. So you compose this one with this one. You compose this one with this one. Minus 8. I'm really hoping now that I did my calculations right. Minus 8 times the other one. And that's the only thing. You can talk about linear adding and scaling diagrams, which is pretty exciting. I mean, now you can perform algebra in diagrams, which is really, really nice. I mean, you will see this in action, maybe not today anymore, and maybe not in this talk anymore, but certainly in the other talks. Okay, the only thing I did is I took this linear extension. So I just now allow formal linear combinations of morphisms. And that's it. This is another vector space. Nothing fancy happens. So if you understand this example and this example, then you're good. That's basically what's going on. And you can do this for any category. It's always working. All properties are basically preserved. So if your starting category is ribbon, whatever, then your linearized category is still ribbon. Pretty good. It's pretty good. It's a pretty good concept. Okay. And similarly, and a concept which is equally good. So this is usually called the linear extension. I could have also called it the linear closure. But yeah, whatever. This is the name, the linear extension. The additive version of it is called the additive closure. And yeah, it's denoted by C and well, direct sum. And what is it? The definition looks a little bit weird. So let me just unravel it. So the objects of my new category, so here the objects don't change at all. Right? Object equals object. And the home space are just linear extensions. The objects now are just formal direct sums of objects from my starting category. Something like that. Just formal direct sums. Anything that is kind of finite. Okay? That's just a new set of objects. Formal direct sums. Don't worry what those symbols mean, they're just formal direct sums. And the home spaces, and in the example it will be obvious, the home spaces are just now matrices of morphisms. Okay, that's a new home space. And composition is matrix multiplication. Let's see how this works. Well, this thing here is just a matrix. So let me give you an example. So if you would have x plus y, this would be a new object, and I could go to z. And x, y, and z are objects from our original category. Then a morphism in my new category here would be, in this case, a 2x1 matrix. Often, maybe I should call this Fij, brackets, whatever, of an old morphism and another old morphism. And F goes from X to Z, and G goes from Y to Z. It's a matrix of morphisms. So, say it again. In the additive closure, the objects are formal direct sums of uh, objects from before, and the morphisms are matrices of morphisms. Um, and why is it called additive closure? You will see the example in a second, but it's called additive closure because if you do it twice, nothing changes. So the additive closure of the additive closure is the additive closure. Anyway, let me go through some examples, and it's with respect to my graded vector spaces. And if you take the linear inter-additive closure, you really get the category of graded vector spaces. Okay, so of G graded vector spaces. Now it's really honestly the category of G graded vector spaces. Objects are graded vector spaces, and yeah, for example, for G equals 1, here you go, it would be just finite dimensional vector spaces. For G equals Z mod 2, whatever you get, it's called super vector spaces or finite dimensional vector spaces. Um, and the corresponding notion here is S. That's the one I will use very often. S direct sum means first linear and then additive. First linear, then additive, right? First linear, then additive. And if this was too quick for you, the only example you need to understand is this one anyway. Okay, so the additive closure of Brouwer, or in this case, oriented Brouwer. I did oriented Brouwer here, works as follows. So now you can add diagrams and you can so the point is, let me say this again, I was too quick. In order to make this work, you want to have, because you need matrix multiplication, you already want to be able to add morphisms. So you start with a linear category. But it doesn't really matter because you can first linearize and then take the additive closure. Okay. Anyway, so for this category, oriented Brouwer, first linear, adding diagrams, linear adding diagrams, then taking direct sums, meaning you have now matrices of diagrams. Right, that's what you see here, matrices of diagrams. So let me do this example here. Okay, so each one of these morphisms, so this funny thing here, what is this? This is certainly a matrix of morphisms. Well, where do we end up? Well, we end up in bullet, bullet, and bullet, bullet. Two copies of it. So it's a direct sum of these guys. And the star is, I actually forgot my own conventions. I think the star is, so the one that keeps track of the orientations is like that. And you start with empty. And how does this work? Well, the first component is your morphism to here, and the second component is your morphism to here. This is why it is a matrix notation. And you can do the same trick the other way, and composition is matrix multiplication. So let's have a look. Matrix multiplication, how does it work? I would take this row and I would compose it with this row, and it will work out. So I just take this thing, put it on top here, and I would need to add, that's what you would do for matrix multiplication. I would need to add the results to, oh, no, this was wrong. Taking this thing and putting it here. So what I would get is the sum of the two circles. Okay, so additive closure means just now you can write matrices of your objects. And really that's it. It's nothing fancy. You just write matrices of your objects. The way to learn this is really, really harmless. I might be a little bit fast right now because I'm really running out of time. I haven't even told you about abelian categories in any way. Um, is the way to learn this is to just uh, yeah, to just look at this example and try to understand it. Okay. Um, the main point about this construction is this proposition. And the proof is actually an exercise. It's not so hard. So let me just go through it. So if you have a category, then a linear category, its linear extension is a linear category. Very exciting. I mean, sure. um, you can always kind of embed a category in its linear uh, in its linear closure, in its linear extension. So you kind of don't lose any informations. And the third point is a really important one. The first two are, if you think about it, it's kind of clear. So if your category is monoidal or anything you want, and then so is that. So all the structures you already had were preserved by using linear extensions. And this really just means that you should do it. You just linearize everything. It's still the same category. But now you can do more tricks with it. And the same works for functors. This is what this proposition says. So if you have a functor, then there exists a unique linearization of the functor such that everything commutes. And same for the additive versions, for the additive closure. And here, similarly, for the additive closure. Almost. There's a slight difference in 2, but the main point in 3 also holds for the additive closure. So neither the linear nor the additive closure really lose any kind of important information of your category. This is what this proposition says, and this proposition says neither the linear nor the additive closure lose any information about functors from a category. There's always a unique extension of any kind of functor. And this inwards, and then I have something like 30 minutes to tell you about abelian categories. This will never work. So whatever. Inwards, what this says is, I will try my best, but we will see. In these words, what these two propositions say is you can do linear categories in everything you want without losing our original category. It's still there. All properties you had on your original category will exist in the linear extension and the additive closure. If something is monoidal, then so is its linear extension. If something is pivotal, then so is its additive closure. So there is no reason not to do it. We could just do it. It basically comes for free. It's a free operation. So free lunch. Right? So this is a free lunch. Free lunch theorem. And this is kind of amazing, right? This really rarely happens. So linear algebra comes for free. Homological algebra is a pain. And that's what's up next. So linear algebra comes for free, homological algebra is a pain. Linear algebra comes for free, homological algebra is a pain. In 30 minutes. So homological algebra in 30 minutes. Good. So I really recommend to read this part. So this is much longer than it's supposed to be because it's homological algebra. It's hard. So you probably want to just read it in the notes, which are of course linked down in the description. It takes a while to get there. So instead of going through all this crap, let me just go through examples. Just do the definitions very quickly and run you through examples. So the first thing that almost never, I shouldn't say almost never, that it's, it kind of rarely exists is the notion of a kernel. So let's say you have some additive category. Okay. So for abelian categories, I always assume that it's already additive. And the point about abelian categories will be the Frey-Mitchell theorem anyway. So I'm kind of skipping through the uh, through the hard part about these definitions here. Okay, anyway, a kernel is something with a universal property. It's a choice of an object and a morphism such that a certain diagram commutes. Okay, good. And there's a dual notion of a co-kernel. And it's just a kernel in the opposite category. Okay, a certain type of object that behaves nice with respect to taking zeros. Right? And having a zero here only works because I'm assuming that I'm already in an additive setup. Okay, kernel is something satisfying universal property. Co-kernel is a dual notion. Okay, universal property means it's unique up to unique isomorphism if it exists. Good. But let's discuss some examples. Of course, in vect, everything is fine, and things as usual kernels and the usual co-kernels. So kernel of a morphism. I will make this very precise in a second for matrices. So you might wondering, wait. A kernel of a morphism is, how is that a pair of an object in the morphism? It is. Just give me a sec. But basically almost nothing has kernels. Like Brouwer, no kernels. Even the linear and additive closure of it, no kernels. Diagrammatic categories, usually no kernels. Of course, then also no co-kernels. But even something easier, even dimensional vector spaces, no kernels. Why? Because basically kernels can be of odd rank. And then you're out of a category. So no way. Kernels are very rare. Okay, but let me try to explain why a kernel actually is a pair of a morphism of an object in the morphism. Okay, and doing this in this easy example of matrices, let's say with rational scalars, doesn't matter. And I'm taking my matrix. Remember that this has objects something like 0, 1, 2, and morphisms are matrices. And so I'm taking my matrix 1, 2, 2, 4. 1, 2, 2, 4. Why not? As you can see, kind of maybe I shouldn't have done that. The first and the second column are certainly not linear dependent. They're certainly not linear independent. Right? The second one is twice the first one. So this matrix would have a kernel, and this matrix would have a co-kernel. Right? And let's see what this co-kernel actually is. Okay. So it would be an object in the morphism such that every kind of crap here commutes. And x and y, let me write it down, are just 2 in this case, because it's kind of, here's my f, right? F is a 2 by 2 matrix, it's just 2. So I would need a kernel, I'm just doing the kernel. The co-kernel is kind of the dual concept. Such that, I'm doing it this way. Here's 0. And I would need something that I can put here. So I need to put an object. Maybe I should do this in a different color. Let me see. Okay, this is my 0 map. And I would need to put an object here and a morphism. And the object I put is 1. And the morphism I put is this one for some a. A doesn't matter. That's a matrix from 1 to 2. And why is it the kernel? Well, this is a kernel because if I compose it with f, I hope I've done my calculation right. Let's see. You compose this with f, you multiply this, and it's 0. So this is really just something that fits here. this was really bad, something that, come on, something that fits here and makes this diagram commute. And the choice of A is you could scale it out, right? You could choose anything. That's why a kernel is actually, in this notion, in this setup, a pair of an object and a morphism. It's an object where your little matrix starts, and it's a morphism. Um, it is all the things you need, all the things that kill your matrix. It's a kernel of the matrix. Dually the co-kernel. And the unique isomorphism for the unique isomorphism in this crap here. So there could be another kernel K prime, right? And another kernel K prime would be a different choice of scalar. Maybe your favorite scalar is 1, maybe my favorite scalar is 5, but they're related by scaling. So the unique map, this one here, would be the corresponding scaling map. Okay. I claim all you need to know about kernels is actually in this is actually part of this example. And then you do some general yoga, okay, classical facts from linear algebra. So, okay, let me just go fast through it, and the proof is diagram pasting, basically. The kernel of the kernel is 0. Sure, if it already dies, and then it will die anyway. The co-kernel of the co-kernel is 0. Just try to write it down for matrices. You will see that this is true. The kernel is 0 for a matrix. Remember, if and only if the matrix is injective, or whatever. If it's monic in this language, the co-kernel is 0 if it's epic, right? It's surjective, injective, and some other crap. It's not so important. The more, well, it's actually very important, but it's best to just write it down in the example above. The morphism K, right here, that's always monic. And the morphism C of the co-kernel, the opposite one, is always epic. And this is a good one. So when is a matrix an isomorphism? Well, if a matrix is an isomorphism, if and only if, it's invertible if and only if, the kernel is 0 and the co-kernel is 0. And this is true in general. Assuming that they exist, the co-kernels, kernels and co-kernels. And you can form a quotient object, just being the co-kernel. That's actually pretty nice. Yeah, we just do it and it works. Very good, very good. And now comes, okay, a very complicated looking definition. It's called the epic monic factorization. In an example, you will see it. It's not so bad. Just do an example. Let me just run you through it. Stay with me. The example will clarify everything. So what is an epic monic factorization? Well, it's a pair of F of some morphism. Well, it's a pair of a monic morphism and of an epic morphism in the following sense. So first, you have a kernel. Okay, you already assume that you have a kernel, and you have a co-kernel of F. Okay. And it's very complicated. You also need, well, it's not very complicated. You will see it in the example. You also need a kernel for this map, and you need a co-kernel for this map. Okay, let's ignore that for a while. You will see it in a diagram in a second. The point is, you have two morphisms, E and M, my monic and my epic morphisms that factor through a certain given object I in the following sense. So here's the diagram. Okay, so you have the morphism F and F on X to Y, and you can factor it using E and M, the epic and the monic. You could factor a matrix into a surjective matrix and injective matrix. That's all that is saying. Um, that's all that is saying. Right? Um, and in general, it has to look like this. Whatever. But this is just factor. Let me just write it differently. Factor F as monic cross epic cross times. This is a really bad times. So circ, little circ. Monic epic factorization. And strictly speaking, it looks like here in definition 3 is 62, 32. Nothing really scary. So yeah, okay. Let's ignore that lemma. It's basically saying that I haven't told you that M is monic and E is epic, but it's basically saying that M is monic and E is epic. It's not just basically saying, it's just saying M is monic and E is epic. Okay, let me do this for you, because if you have uh, uh, so you can also define an image in the following universal way, but let me just do it in the example of matrices, because this is really the example um, of this one and of this one. Okay. So same setup as before. I take the same matrix. So how can I factor this matrix into an injection and a surjection? My F is neither, right? My F is neither an injection and a surjection. And what I can do is the following. I can write down F as 1, 2, 1, 2. So this is surjective and this is injective, as you can see. I mean, this has no kernel. This has no co-kernel. And if you do the multiplication, you will see that this is exactly F. And F equals is exactly the definition you had above. So F was equal to M times E. Yeah, and that's really the epic monic factorization. And how do you get this morphism here? Well, it's a corresponding thing for the image. So what is the image of F? Okay, the image of F is again a pair of an object and it's the M morphism from above, such that a diagram very similar to the diagram for the kernel commutes. Very good. And in this case, the image, so again, remember you have a map from 2 to 2 and it's called F. The image is this thing. No, this is the other one. The image is this thing. Oh, no, not this color. And there exists unique my epic morphism, and the image consists of my monic morphism. And what could it be? It's exactly whatever you hit with F, right? So up to scalars, you could, for example, take for F the first column, and that's what I did as an image. And the epic monic factorization, so the object I from above here is really the image. Right? I hope that makes some sense. Similarly, something like, well, some homological algebra. So if F has an epic monic factorization, then the image is the I from above. Anyway, and the usual nonsense, it's unique up to unique isomorphism, whatever. So this is not so super important. So okay, I think I stop here because I'm running out of time, and I just split the lecture into two. So there will be a second video when I will tell you more about abelian categories. So I think that's it for now. Let me wrap up what I said. Basically, discuss the notion of what it means to have linear algebra in categories. We had the linear categories, additive categories, and they had these nice envelope things. The linear extension and the additive extension would basically come for free. So everything you have seen, um, everything you have for your given category will be still present in those extensions. So kind of linear algebra comes for free. Then I showed you a little bit about kernels and co-kernels and images and whatever. And the, all of this will basically be the main ingredients to define abelian categories, which, as I said, we'll do in the second part of this lecture. Yeah, and that's it for today, and I hope to see you next time. Bye.